السلام عليكم ورحمة الله وبركاته. يسعد صباحكم يا شباب. اليوم إن شاء الله حنستأنف معكم التجارب لهذا المختبر، مختبر خواص المواد، وإن شاء الله هغطي بالتعليم عن بعد المحاضرات النظرية، وإن شاء الله لما نرجع على الجامعة نعمل الجزء العملي إن شاء الله. إحنا قبل ما نعطل وندخل في حالة الطوارئ وصلنا لتجربة رقم 7 experiment number 7 which talks about heat treatment. Okay, so heat treatment, and in more details we'll talk about quenching, normalizing and annealing of carbon steel. Okay, so هذه الأسماء later on لازم تحفظوهم زي اسمكم، انتوا already بتعرفوه. Okay, as a very quick revision للإشي اللي انتوا عارفينه. Okay, steel is one of the most used engineering materials. Why we use steel a lot? Because it's everywhere. Okay, متوفر, abundant in the earth. Okay, so it's used in the form of beams, plates, tubes, sheet metal, wire, special steel, cutting tools, etc. Okay, so they used this substance everywhere. Why? Because it is there everywhere. Okay, so usually you heard certain word which is iron, then you heard another word which is steel. What's the difference between them? So iron, it is abundant in the earth, as we said, in the crust of the earth, in the form of Fe2O3, and it's very easy to convert it to Fe. So, okay, now when we can call iron steel, if it's mixed, so if iron that contain a small amount of carbon, so usually less than 2%, we can call it steel. Okay, so it is not pure iron, it is iron with certain carbon. The properties and microstructure depends on the carbon content, as we'll see in the coming slide, and the thermal history or the heat treatment. Okay, so we can judge the microstructure and the properties. Okay, the behavior of this metal. So it depends on the carbon and the thermal history. So the property and microstructure of steel, okay, depend on carbon and thermal history. Here we have phase diagram. This is very famous diagram. Okay, and this is cover the iron carbon substance. Okay, so here in the x-axis we can see that it represents the composition. Okay, which is represent the percentage of carbon atom in the iron, with the iron. Okay, so here, for example, if we are here, that means we have 0% of carbon, and here we have the maximum amount of carbon, which is 6.7 percentage of carbon. Okay, and of course here in y-axis we can see this is the temperature. In the secondary y-axis we'll see temperature in Fahrenheit. So we care a lot about the composition and the temperature of this phase diagram. Okay, you can also notice that we have here single phase, here we have single phase. Okay, here we have two phase. We'll talk a lot about all of them. Okay, now also here you can see this point, we call it eutectic, and this point we call it eutectoid. Okay, what do you mean by eutectic and eutectoid? Eutectic during cooling change from one liquid phase to two solid phases. This is what makes this point special. We move from liquid, if we are going like this, if we are cooling down. Okay, so we are moving from liquid from single phase to two phase. Okay, austenite and cementite. eutectoid during cooling change. So here, if we are cooling down, it will change from one solid phase to two solid phases. Okay. So in the eutectic, we are moving from liquid during cooling to two phase. Okay. Two solid phases. But in the eutectoid, we are moving from solid, not from liquid. Okay, from solid to two phase or two solid phases. Okay, which is cementite and ferrite. Now, type of phases in steel. Okay, so let us see the type of phases. How many phases we have? What's the difference between phases? Okay, in steel we have the first phase, which is ferrite, alpha iron. Okay, so this phase is stable up to 912. We can see here from the phase diagram. So here we have the ferrite, okay, and it will be stable up to this point. Okay, here we can see that we have ferrite. Okay. Okay. Now, it has BCC structure. Okay, soft in a pure state. So this is the property. And it can be dissolved up to 0.022% carbon. This is the amount or the composition of this phase. It has 0.022% of carbon, which is very low percentage. Okay, and this is the phase diagram. This is what we can see under the optical microscope. Okay, you can see here the grain, and the dark or the black lines represent the grain boundary. Okay. The second phase of steel is the austenite gamma. Okay, stable between 912 up to 1394, and it has FCC structure. Okay. In the previous experiment, we relate those phases to the behavior of the substance in terms of toughness, ductility. Okay, remember? And this is the microstructure, okay, of this phase. Cementite, or we can call it iron carbide. Okay, this cementite, if we go to the phase diagram, we can notice that it has the maximum amount of carbon. Okay, 6.7%. Okay, but cementite can contain up to 2.14% of carbon. This phase, due to high percentage of carbon, it could be hard and brittle. Okay, and it has a complex structure. So this is a summary of the three phases we demonstrated. Okay, so we have austenite, gamma, alpha, and cementite or iron carbide. Okay, the composition, this is between 0 up to 2.14% of carbon. This is up to 0.02, and this one 6.7% of carbon. Okay, and this is very important regarding strength and activity. This one, because it has the highest amount of carbon, this is extremely hard, and at the same time it is very brittle. Okay, so in terms of ductility, the austenite is very ductile. Okay, and in terms of strength, it's very low. So this one represents the average behavior in terms of strength and ductility. Another phase is perlite. Okay, this is a fine mixture of ferrite, okay, ferrite and cementite, Fe3O, Fe3C, okay, iron carbide, okay, and forming as a result of the composition of austenite at a slow cooling condition. Okay, so for example here in the eutectoid point, if we have austenite, we have substance at this temperature, very high temperature, and we're cooling down. Okay, so we'll reach up to ferrite and cementite. Okay, so but when this happen, if we have what? How we can obtain perlite if we have slow cooling condition? Okay, we have slow cooling condition from austenite temperature, so we'll have ferrite and cementite structure. And under optical microscope, we'll see this structure. Okay, so this structure is contain black lamellae. Okay, the Fe3C iron carbide, and their thickness in a few micrometer. So here we can see this lamellae with. So this perlite, another phase of steel, and this phase appear when we are cooling down very slowly from austenite temperature, and we can obtain passing through eutectoid void. Martensite, another phase. We can get this phase if we have very rapid cooling, and we are moving from this from this structure, okay, into BCT, body-centered tetragonal. Okay, and this phase is extreme hard. Okay, extremely hard. Okay, so this martensite very hard and at the same time very brittle. Okay, and this phase appear when we have rapid cooling from the austenite temperature again. Okay, and here is the microstructure. Okay, so types of steel in terms of percent of carbon, if we have exactly 0.76, then we have eutectoid steel. Okay, if the percentage of carbon less than 0.76, then we have hypoeutectoid steel. If the percentage of carbon greater than 0.76, then we have hypereutectoid steel. Okay, so if we are passing through this point exactly, this is eutectoid steel. If we are here, this is hypo. If we are here, this is hyper. Okay, and here is the microstructure, which we call it perlite. Okay, you can see the perlite. Okay, so this is Fe3C if we have very dark area, and if we have light area, okay, this is ferrite. Okay, now the hypoeutectoid to the left of this point of 0.76, okay, and it consists of perlite and protectoid ferrite. Okay, protectoid ferrite, perlite and protectoid ferrite, those larger area. Okay. Hypereutectoid steel, so we'll have perlite and protectoid cementite. Okay, protectoid cementite, perlite and protectoid cementite. This is very important. You have to memorize it. Okay. If we're passing through this eutectoid point, we have only ferrite and cementite, which we call it perlite. Now, what is heat treatment? Various metallurgical process that involves heating and cooling. Okay, it's done in furnace. Why in furnace? Because we are control the environment of the furnace very accurately. Okay, so the heating process should take place slowly in order to minimize distortion. So in this experiment, we'll heat the specimen up to 900 degrees Celsius, and this heating happens slowly. Why? Because to minimize distortion. Okay, to minimize distortion. It's performed to affect structural change in the material which in turn affect its mechanical properties. Example of heat treatment, we have quenching, annealing, normalizing. Okay, so in this experiment we'll see this type, quenching, then we'll see annealing, and we'll see normalizing. Okay, and also we have tempering and surface hardening. Annealing, what do you mean by annealing? We'll have annealing, okay, if we are doing very slow cooling. Okay, heat treatment in which material is exposed to an elevated temperature, usually we call it austenitic temperature, okay, for an extended time period, and then very slow cooling. Usually this annealing happens inside the furnace. Okay, once we reach 900 and leave it for a while, then we'll turn off the furnace and leave it to cool very slowly. Okay, so usually this process takes like 24 hours. Purpose, relieve stresses from the specimen, increase softness, ductility, and toughness, produce specific microstructure. The microstructure produced in the annealing, okay, is coarse perlite, okay, in addition to protectoid phase. This is very important. This is regarding the resulted microstructure. Coarse perlite. This is time consuming. It takes like 24 hours to cool down. The microstructure yields having a small grain, very small grain, and uniform grain structure. Usually the cooling rate 1 degree Celsius per minute, very slow cool. Normalizing, heat treatment that is used to refine the grain, and or that is used to decrease the average grain size, okay, comparing to the quenching, and they produce a more uniform and desirable size distribution, fine grain perlite, and also comparing to annealing, are tougher than coarse grain one. Okay. Yes. The cooling rate faster, between 5 to 10 degrees Celsius per minute, and usually this is done by taking the specimen after leaving for like 2 hours in furnace when we are heating it at temperature of 900. Then we'll take it out and put it in the still air. Okay, so this is what happens. So the cooling rate here faster. Reduce fine perlite, as we mentioned, structure, which which has higher strength and hardness than product of full annealing. So this one reduce better property in terms of strength and hardness. Okay, and also in terms of structure, fine. In annealing we have coarse. Quenching, this is the third type. It's a process where a metal is heated at a temperature above transformation temperature. Usually in 3 types we heat the specimen up to austenitic temperature, 900 degrees Celsius, as we'll see in the manual. Okay, and then quenching by immerse the specimen in oil or in water. They submerged until they are cooled will cause metal to be hardened, and the resulted microstructure is martensite. So, consisting of 2 steps, heating the steel to a sufficiently high temperature for a long enough time to convert it entirely or partially to austenite. Then quenching, cooling the austenite rapidly, very rapid cooling, okay, enough to avoid passing through the TT curve, the nose of the TTT curve. So here we have a quenching medium. We'll use water and we'll use oil. Okay. So here the hardness normally less than water quench. Okay. And we'll see what is the effect of it is gentler than the water, okay, and we'll see the effect of the water quenching compared to oil quenching in terms of grain size and in terms of hardness when we'll do the experiment. So this is the austenitic temperature, and we'll move to perlite, bainite, and martensite as a result of cooling. So this is the austenite temperature. We can go to martensite by rapid quenching. Okay, we can go to bainite by moderate cooling, which is normalizing, or we can go to perlite and eutectoid phase using slow cooling, which we call it annealing. Okay, so this martensite. So this is the experiment 7. Okay, if this is extra, if we reheat the martensite, we got the tempered martensite. So let me show you the. So here is the manual. Okay, experiment number 7. So this is the title: heat treatment, quenching, normalizing, austenizing, and here is the apparatus. We need a high temperature furnace. Okay, we need Vickers micro hardness testing apparatus in order to measure the hardness, Vickers hardness number. We need optical microscope in order to examine the microstructure. I think this step in your case we will not do it, okay, because of time limiting. And we need 4 plain carbon steel specimen. Okay, so here is the procedure. You will do it. Once we are ready, then we'll have the 4 specimen. Okay, we have original specimen. We'll measure its Vickers hardness. We'll measure diameter 1, diameter 2, and then we'll obtain the Vickers hardness. We'll do the same for water, for oil, for air, for furnace. Here are the 4 specimen, and this is specimen number 5. Will not do any heat treatment. So those 4 will do heat treatment, and this one will not do anything. Okay, and we'll compare between them. So you need to answer those questions. So that's it for experiment number 7, and also today we'll talk about experiment number 8 in the coming video.